Okay, welcome to the afternoon session. Our first speaker this afternoon is Barbara Grosz. Barbara is the Higgins Professor of Natural Sciences in the School of Engineering and Applied Science at Harvard University, and she's also ex-dean of the Radcliffe Institute. Barbara and I go back a long time. Barbara's known for her contributions in the fields of natural language processing and multi-agent systems, for which she received the ACM AAAI Alan Newell Award for fundamental contributions in these areas. Besides her research, Barbara served as chair of Harvard University's Task Force for Women in Science and Engineering, and then went on to serve on the National Academy's committee that produced the excellent report Beyond Bias and Barriers, which I recommend to you on women in science. So without taking up more of Barbara's time, her question for today is, what question would Turing pose today?
Thank you, Bonnie, very much. So I think I can take it as a reasonable assumption that everyone now knows that in 1950, Alan Turing wrote a landmark paper in which he asked the question, can machines think? And then almost immediately dispensed with that question, saying that both the terms machine and think were too ambiguous. He proposed instead the imitation game. And essentially what he was saying is, I can't answer this question, so instead of trying to define terms and answer that question, I'm going to see if we can imitate human behavior. As I hope you understand from both David Harrell's talk and also Elfan, whose last name I'm not sure how to, Chafi's talk, a key aspect of this proposal was that it was an interactive test. And we can see that that notion of interactivity is playing a role not only in what I'm talking about, but also in computer security and many other places. As we also heard this morning, there's no small amount of philosophical debate about whether the imitation test is really the right test for artificial intelligence or for a machine being able to think. And I want to note that Turing took thinking and being intelligent to be the same thing. So he wasn't aiming for being a rocket scientist or a brilliant mathematician. He was really equating thinking with intelligence. I'm not going to go into that debate today. Instead, I want to look at the question he asked and at some of the things he said in this mind paper, take a status check, and then look at where we are today. So this is in some sense in the same spirit as Steve Ferber's talk, but I will be talking from the perspective of research in artificial intelligence rather than in hardware. The paper, every time I read this paper, I find something else that's absolutely brilliant in it and predictive of not simply where we are now, but of the path that's been taken since the paper was written. So this is perhaps the most famous extract, other than the description of the imitation game. This is where Turing predicts that in 50 years' time, so the year 2000, he thinks that a computer will be at the state where it will be only, where the interrogator in this game will have only slightly more than chance possibility of making the right identification of the machine and the person. The one thing Turing was right about was the gigabyte size of storage. He hit that one approximately right, as we learned this morning on other predictions about the computers and their speed. He had no idea where we would be now. It's also important to note that the test itself was a test of behavior. So Turing isn't looking inside the machine. He's not looking at mental state, and I'll come back to that in a bit. Immediately after Turing makes this first statement, he makes this statement that you see here, and I've highlighted in bold what I think is most crucial here. His prediction that we'll be able to talk about machines thinking without being contradicted. There's no question that not only today, but even in the year 2000, machines were behaving in ways that were so seemingly intelligent that people not only spoke of them in some senses being smart and intelligent, but they yelled at them when they didn't act smart and intelligent. And that's, in fact, since it's after lunch, I'll ask, if you've ever yelled at your computer, raise your hand. I just wanted you to, get some activity going. So this he was exactly right about. Now, some of that has to do with our psychology and our willingness to attribute to all sorts of inanimate objects smartness, but he was absolutely right about that. There are many other things he says in this paper, and I won't have time to talk about all of them, but I've highlighted a few that I think are lessons even for today. And one of those is his research program advice. So after he has talked about learning machines, and I'll come back to that in a minute, he ends by saying it's not clear whether we should try to get the machines to play chess or to do something else. But he ends by saying, I don't know what the right answer is, that the funding agency people should pay attention to this. I think both approaches should be tried. So he wasn't trying to predict ahead of time how you were going to get there. I also want to note, as someone who has done research in natural language processing, that one of the lessons from the early days of artificial intelligence is that some of the things we take for granted as people, like understanding language, are actually a lot harder than playing chess. So really thinking about thinking and taking, not thinking about what it's hard for people to do, but what it's easy for people to do, helps us focus on what I think Alan Turing was getting at. So I mentioned that there are many systems today that are spoken of as acting intelligently. You probably have read about all of these, or either read about them in the press or you use them. So Deep Blue, the chess champion, cars that now drive around the desert and to some extent in the city on their own, a system that will find the music like the music you like. We all take advantage of search engines. How many of you watched Watson play on the Jeopardy program? So there's another example of something that Turing would have been very happy to see. And then there are many other systems which we use every day, banking and credit card systems. I want to stop actually before I go to my next slide and salute the University of Edinburgh and its program in informatics and computer science, because it, like those around the world that did basic research in computer science and artificial intelligence, laid the groundwork for all of this. So we see this, but for example, Watson takes great advantage of all we have learned about natural language processing and all we have learned about machine learning in order to do what it does. Without that basic research, we wouldn't have any of these systems, and the same is true of the driverless cars and Deep Blue and the search engines we all love. So you probably know about all of those. You may not know about airport security, and I want to just, this is work by Milind Tambe and his group at USC. If you fly through LAX, you can rest more assured that the guards that are looking for people who might be driving in with packages you don't want them to leave at the airport are actually being detected, because instead of using a human randomized strategy, which is, well, let's do the terminals in the order 1, 2, 3, 4, and then again in the 1, 2, 3, 4, it's actually using technology from game theory and multi-agent systems to figure out where to assign guards, because they can't assign them everywhere. So that's one place this is being used. They're beginning to test this with the Coast Guard looking at ships coming in. And so that's all keeping us safer. They're also looking at adapting it for protecting tigers in the wild and for protecting forests that are at risk. So another set of applications of basic AI that is changing the world that we're in. So I said that we can all applaud that these are really great advances in the field of artificial intelligence, making it out into the world, systems that we all think of as acting intelligently until they don't. And perhaps one of the most well-known examples now is Watson as it played Final Jeopardy when asked about what US city had two airports, one named after World War II battles, answered, "What is Toronto?" There's actually, next, if you ask Dave Ferrucci, he'll tell you why this happened. If you find people who are baseball fans and have forgotten that Toronto is in Canada, they might have made the same mistake. Okay? It's in these kinds of errors, that are errors that we can say most people wouldn't make, that we can see the fragility of these systems and the sense in which they aren't yet really thinking in anything that could fool us into thinking that they're like people. And I want to come back to, at the end of the talk, when I ask what Turing would ask now, I'm going to come back to what behavior it is we might now think about asking whether computers are capable of. So let me, that's kind of a state of where we are. I want also to highlight a few other things in Turing's paper. First, he noticed many of the criticisms that would be put forward in terms of even trying to build machines that were thinking machines. And many of the philosophical arguments revolve around some of these same issues. The paper itself is a whole section in which he answers all of these possible critiques of the imitation game as a measure of a thinking machine. One of my favorites is when he answers Lady Lovelace, who essentially puts forward that computers will do whatever we tell them to do, but they won't surprise us. They won't do something we hadn't directly programmed them to do. Turing's response will be familiar to many of us today. We often are surprised by our computers. Occasionally, we're positively surprised as opposed to negatively surprised. And Turing himself was after those positive surprises, not the negative ones. He also has a very interesting answer, which is here, where he's saying, well, you know, Lady Lovelace just didn't have evidence that would show her that computers could do this. She doesn't have a proof that she can't, but she didn't have the evidence ahead of her, in front of her, that would suggest that they could. I do want to note that in addition to this particular mind paper, there are other documents available that give you a sense of Turing's state of mind about the test. And these are all actually collected in Stuart Schieber's book on the Turing test, where he brings together all of the Turing papers and the philosophical arguments. Two of the things that are noteworthy are that if you look at some of those interviews and read some of the unpublished papers, you'll see that Turing later changes from 50 years from now to about 100 years from now. So we still got a while for the computer to pass the Turing test. And he also mentions, related to this, that we should be careful not to claim that the originality is implicit in the rules, that we should be willing to take something novel as coming from the computer behaving in a way we hadn't anticipated as its own novelty. Another important element in the paper, for many people think that randomness is a relatively new idea in computing and in theoretical computer science. Actually, it's in Turing's paper. He talks about a random element in the computer itself, and just in general in building the computer. And he talks about randomness being essential for learning. These things have also turned out to be true. Randomness, as we heard earlier this morning, is very important for computer security, and it's turned out to be important for many of the machine learning algorithms that are used today. So this really was a paper for the century. He does suggest that we won't be able to build a computer that can play the imitation game well if we just try to build in the adult mind, and suggests instead that we begin by having a child program and we teach it. And he also has the notion of reinforcement learning in the paper because he talks about rewards and punishments. So I also want to stop here to comment on his notion of learning, because I'll come back to that later also, because it's essentially teaching directly, telling the computer facts, and then running the program, seeing where it doesn't work, and adjusting the program. By the way, that's how that's how Watson got so good at Jeopardy. They ran it on Jeopardy examples. When it didn't do well, they changed what they were doing, so it was that kind of iteration. This is not, however, how children learn. Children learn by playing, by experiencing the world. From the very earliest days, and Liz Spelke's work has been really wonderful in showing this, children are interacting with people and learning from those interactions. So the way we learn is, in fact, by interaction with others and interaction with the world, again, from a very early stage. This is something that I think Turing wasn't aware of, or he might have thought about the learning process somewhat differently. For anybody who is a fan of logic or has worked on theorem-proving systems, Turing also has some wise words here, where he talks about logical inference and two things. One is the machine is unlikely to do it exactly the way that we do it. And the second is that the order in which you invoke the rules is going to turn out to be crucial, as we have all found out in trying to develop these systems. So, if we just done a careful reading ahead of time, we might have avoided a lot of mistakes, but maybe they were necessary too, as in learning in general. So this was a paper for the century. It really was absolutely stunning in laying the groundwork for computer science in general and artificial intelligence in particular. But it was very much a paper of Turing's times. So I mentioned what we now know about infants and how they learn, and young children is very different from the picture he had. I think on analogy that if you look at very early paintings of children, they're drawn as though they were adults with small bodies. It's only really relatively recent in the history of art that the difference in children is really portrayed well. And his idea of learning was, well, it's like you have a little adult without enough information and you pour more in. So there was a difference. Psychology was very much rooted in behaviorism, which is probably why we got an operational test. It was good for us that we got an operational test because that's what you can do with a computer system. But also, and I think crucially from the point of view of how we think looking forward, the way computers were used when Alan Turing was here was very much one-on-one. One person using the machine. You were lucky. I mean, you needed the whole machine. As we heard earlier this morning, there wasn't much there to be used. And it was in command mode. And that's very much not how computers are used today. So we've heard about advances in brain sciences and in hardware this morning. Computer science, of course, has, as a field, moved forward enormously. We've also come to appreciate, I think, in a much deeper way, that the way in which a computer might process information, the methods it uses don't need to echo the methods that people use. And I think we've all come to appreciate that people and computer systems have different strengths and weaknesses. So one of the things that's just wonderful about the search engines is that computers are actually a lot better at searching than we are. And they're especially a lot better at searching through large repositories of information. They're also better at doing certain kinds of analytics. So that as we look forward, and that's what I want to do next, as we look forward to think about what question we might pose today, I'm going to look at what computing environments are like today. So the next 3 sections of the talk, I'm going to briefly talk about computing environments today, talk about some of my own work on building collaborative assistance and on computer decision making, and then at the very end come back to ask the question in the title of the talk. So this is a much more typical computing environment for today from the one that Alan Turing had. You'll notice that there are little machines here, though we've got a laptop up here. But what we've got is a mixed network. We've got people, we've got different kinds of machines working together to get a job done. And thanks to the advances in hardware and software and algorithms, we really can work at a normal working speed with computers helping us to get things done. So this is radically different from one person issuing commands to a computer. So the work I forgot that I added this little laptop in. So the work I want to talk about is about having the computer reach out and really be a partner in these endeavors rather than still being in this mode of accepting commands and being a somewhat dumb servant much of the time. So if you think about that network, and it goes back to what I said earlier about children and the way they learn, which is that the system is in the context of working with others. So it's not new that we should look at collaboration and think about collaboration as the basic mode of operation. I've put these 2 quotes up because they talk about how it's fundamental to language acquisition that infants are involved in that kind of interaction and collaboration with parents and with others from the very beginning. And I wanted to do that because Turing's test is the Turing test is a test of verbal behavior. So you might have thought you could isolate verbal behavior from social interaction, and you absolutely can't, even in the very origins of learning language. So the goal of the research that I'm going to talk about is, as I mentioned, is to get beyond the screen-deep interaction and to build into the computer system collaborative capabilities. I'm going to talk first about a little bit of research that talk a little bit about a fair bit of research we've done on collaborative assistance, and in particular, I'm going to focus on research that we've done on interruption management. So here's a slide that gives you kind of a sample setup for the kind of application that I'm thinking about. You have multiple people and multiple computer agents helping people in getting a job done. What I've shown here is travel planning, but you could also think about scheduling meetings, organizing healthcare, support systems for any kind of team effort, including healthcare and rescue team support. So what I've portrayed here is 2 different individuals. There it is. 2 different individuals. They may need to communicate. Agents may need to communicate with them. And the question that we've been asking is, when is it appropriate for a computer agent to interrupt a person? Most of the time, dialog boxes pop up. At times, we would rather they didn't. Again, I could ask you, how many people here have wondered, why on earth did it ask me that now? Just go away. So can we build systems that are more sensitive to when the cost of the interruption is less than the value gained from it? We've looked at this from a number of angles, including formal models and for collaboration and for reasoning about collaboration, and models that look at human behavior. And I'm going to talk just a little bit about a piece of work that falls on the left side of this diagram. where essentially, I'm going to do this quickly because I noticed the clock. We're going to look at decision theoretic rules that decide whether to interrupt, and we view interruption as a kind of helping, based on whether the expected utility of the information to be gained is greater than the cost of the interruption. So you can think about an example where the computer agent is working with you as you drive home from work and trying to figure out whether it makes sense to let you know about an errand you could run on the way. The computer doesn't know what route you're taking, but it has some notion of possible routes. It then learns that there's a traffic jam on the route you're most likely to take and asks the question of, should it inform you of this or not? In order to do this reasoning, we had to look beyond representations of plans, even representations of plans for collaboration, which we had developed earlier, to think about layering over it information about the probability of a plan that someone else is following. So we had developed this notion of shared plans where you could mesh together the plans of multiple agents. But crucial to that is my being able to guess about how you're doing some part of your activity so that I can decide whether to help you or whether you're going to interfere with what I'm doing. So you see an example of the representation for that here. The important part for what I'm going to talk about is that going the normal route from this representation, you might guess that it's going to take about 20 minutes. Once you learn, or once the agent learns that there's a traffic jam, that normal route goes up to 48 minutes. So most of us would say, yeah, let me know about this. Okay. And tell me to take the other possibility, and you see that in the flipped probabilities here. So I have just said essentially this, that the decision to communicate is going to be, is going to be based on the cost versus the utility. We tested this out in a testbed system that we developed called Colored Trails, where essentially the players move around on a board headed toward goals. They do that. You can't move your piece unless you have a chip of the right color to move into the square. I'm not going to go into a lot of details about this. I did put up the web page because we're happy for people to take this and play with it. The most novel use of this game was as a test of cognitive decline in the cosmonauts who were stuck away somewhere for 3 months. They had them play this on a regular basis to see if there was any effect. I haven't seen the results of that yet. Okay, here we use this differently, though. We essentially did a model of this kind of situation by placing two different players on the board, R and O, with different goals, and putting on the board some traps. And we set this up so that O, you can think of O as the agent, could actually see where the traps or the traffic jams were. And R, you can think of this as the driver, does not see where they are. R, on the other hand, knows what resources it has, and O doesn't. So there's partial information on both sides. And we asked the question of whether doing a decision theoretic approach to either informing or asking would work better than always informing. This is what the dialog boxes do. They always tell you, even when you don't want to know, or never informing. And just to give you a quick summary of one take on this, this is holding cost constant. We actually varied cost. What you can see is if the world uncertainty, that is how fast the traps are coming up, is low, and the observer uncertainty, that is how little the observer knows about the chips the other agent has, if they're both low, then informing is significantly better than asking, because essentially the world's not changing much, and if you look at asking, you're asking far too often. In contrast, in a situation where both uncertainties are high, so the world's changing very rapidly, but so also, but the observer, the agent, is unsure about the resources of the other, then waiting to be asked is better. But most important, the decision theoretic informing and asking everywhere perform better than just doing it either all the time or none of the time. So that's a snippet of that piece of research. And I want to that's where we are using computer agents to explore the kinds of behavior people would find acceptable in an agent and to build agents that are more helpful to people. The second piece of research I want to talk about is actually looking at how people behave and using that to build agents that behave better. And this is work that was done recently by another student of mine. The first piece of work was done by Kamar, who is now at Microsoft. Dimitrios is going off to Google. I think there's a lesson here, but I just have to get them both back to the university at some time. Dimitrios' hypothesis was that if we understood how to deploy the positive aspects of emotions in people's decision-making, we might be able to improve agent decision-making. And again, I have a quote from Psychology from a long time ago. So essentially what he did was to adopt the Ortoni, Clora, and Collins approach to modeling emotions. This was developed in the I guess in the late 80s, actually. It's the first architecture that took the positive, well, they looked at both sides, but the role of emotions in affecting decision-making. And the essential idea, it's an appraisal theory of emotions they used, is that something happens, you look at how whatever you experience how that relates to what you're trying to get done. That yields some emotion. In people, that has a variety of effects, but one of the effects is that it changes your goal structures. And that's the particular effect that Dimitrios was interested in. Oops. So this is 2 examples of how that might work. And we looked at that in 4 different settings. 2 of those had to do with communication to people, and communication and coordination within groups of agents. And I'm not going to talk about this one. A third one had to do with decision-making by a single agent. So I will only give you a snapshot of those results. What was done here was in a multi-agent system playing a couple of different canonical computer multi-agent scenarios. The agents had a priority of goals set up. If they experienced something like anger or fear, they would readjust the priorities. By doing that, they could use much more short-term decision-making rules and perform better. So it actually worked to reprioritize the goals and then be able to look a shorter distance out in doing your decision-making. In this study, what we looked at was whether groups of agents that signaled emotions would actually coordinate better than groups of agents that didn't. And the answer here, again, was yes, and that, in fact, using the shorthand signal of an affective state was as efficient in terms of performance as communicating full state. So those are 2 little snippets of research in multi-agent systems leaning in the direction of building computer systems that are more collaborative and better decision makers. And I want to come back now, so that's a very broad view of the research, come back now to Alan Turing and to the question of whether digital computers can think. This is from a transcript from his BBC interview shortly after the paper came out. And this reflects also on this morning's talk, several of this morning's talks, where Turing himself says, the process of thinking is mysterious. I think trying to build a machine that thinks will not only change technology, but will help us figure out more about how we ourselves think. And I would take that as a theme coming out of several of this morning's talks, and I hope out of my talk. So let me turn now and say, with that in mind, and this computing environment, which also I think Turing never would have imagined. I mean, people were using computers to do mathematics. The idea that the heaviest use of computers would be for communication and for coordination and for helping us get done our tasks, many of which are thought tasks, I suspect wasn't at the forefront when he came up with his test. So if you think about that question and think about this, a setting like I've shown, I'm going to make a proposal and then I'm going to ask you the question. I'm going to make a proposal that Turing would have thought not about sitting in the parlor asking questions, one-time interactions over repeated subjects, where in fact you can argue, as the philosophers have, the constraint of the imitation game is both too strong and too weak. But he would have thought more about this kind of scenario. And he might have asked a question like this: can we build a computer team member that would behave in such a way that people wouldn't notice it wasn't human? And it's not that it would mistake the computer for a human, but it wouldn't make the kinds of mistakes that set our teeth on edge. It would behave as seamlessly with us as we do with each other, which is not to say perfectly. It would do that well enough that we wouldn't react to it by saying, oh, how stupid. How could it possibly have done that? I want to note that to succeed here, and this is actually, in some ways, echoes very much David Harrell's idea of the full organism. You're operating in an environment. You have to have models of others, okay, which is all part of how our intelligent behavior works. It's a dialogue setting, not an individual question setting. So that's one possibility, but I'd like to know what you think. What question do you think, from the work that you're doing, Turing might pose now? And I leave you also with these two wonderful quotes from Alan Turing himself. Thank you.
Just as in the morning, we have time for questions. Okay, they'll be coming around with the microphone. Thanks, Claire.
Thanks for a great talk, and I completely agree with your last question, which I believe is one of the more important ones we could address. But the difficulty it has, unlike the original question, is that it's very hard to say yes or no or this much and so on. Do you have any thoughts on how you would establish that this is happening?
Well, I do, and I'll tell you. I'll answer first with an anecdote, and I picked the word notice for a reason. I think that we notice differences that are really crucial to us. And the anecdote is that when the first year that I was at Harvard, I walked by the Science Center at Harvard, which is where their big events and the big lecture halls are. And I noticed that the list of public speakers for the year had no women on it. And I noticed that as I walked into a meeting of the, quote, executive committee for this group, which I had been asked to serve on. And we were going to pick speakers for the next year. So I mentioned to the people in the room that there were no women. And they said to a one, oh, we never noticed. So I think that actually is an important test. It's not a 5-minute test like Alan Turing's, but I think we could come up with a measure of it that might have to do, it would again, you know, it's all frequency, which his was, by the way, also. He's not asking for perfection here. He's not asking 50-50. He's saying just to get it up to 70. So I think it has the advantage over the imitation game that getting partway there, you can also measure getting partway there, and that trying to get there is taking you on a route to getting there. which I think, and there are criticisms of the original test that it's actually not taking us in this direction.
Other questions? Well, I'll ask a question in the meanwhile. One of the things one of the quotes of Turing that you pointed out was that he said it may be best to supply the best sense organs money can buy and then teach it to speak English. So he's not acting like a mathematician who's saying that we're working on a command line. I'm wondering whether you think this is a result of the behaviorism, the stimulus response, and that you need stimulus, or that he had a much deeper view of language as coming out from its grounding in the world.
So I wish the latter, but he was behaviorism was just there. I think that there are many reflections in what he wrote that it was really stimulus and response. I'm sorry.
Too bad.
But it also, I think it's really credit to the enormous amount of research that has happened in all of the cognitive sciences and to the crosstalk among them that we know. Now there are cognitive models and mental models, and we haven't gone from souls and consciousness to stimulus response and saying there's nothing in between. But I don't know. I wasn't there, and I'm not an Alan Turing historian. Yes, Mark.
So I like your new version of the Turing interaction. The thing that makes that most hard, I think, and the thing that people always notice is that as machines approximate that kind of behavior, they let one down on making the kind of inferences about everything that's going on in your head that human beings use so much when they collaborate. So can you comment a bit on the progress that we're making on that kind of problem?
So I agree, but that's why I think this is, so first, I really do want to hear from people if they have ideas about what question to ask, but let me answer that. That's an absolutely crucial part of human intelligence, of thinking, is to think about the other people. And it's why I put up those quotes from infants. Actually, two of my fellows at the center this year are people working on autism, and the pointing, and we saw that this morning, the pointing doesn't work the same for kids with autism. So those models of other are absolutely crucial, and it's not stimulus response. What progress are we making there? Well, we've got a long way to go. That's about the best I can say. I think we have a long way to go in the neurosciences. Things like mirror neurons, what exactly those mean. This is a place where I think there's work to be done in neuroscience, in physiology, in medicine, as well as in computing. I think it's actually, to get back to Steve Ferber's talk, it's one of the places where we know the least, at least someone will correct me, really, about how we do it ourselves.
Okay, one more question.
Forgive me if this seems a bit of a distraction from Turing's original question, but it's often surprised me as a biologist that people working in artificial intelligence seem to want to go directly to human. When we didn't build Concorde first, we built the Wright brothers type of plane first, and we built a Firework, not the Saturn V rocket first. And it often surprised me that, although I understand it's easier to perform the tests with humans because we interact with machines, that we're not trying to get the cognitive skills of a fish or of a dog sorted out first, before we try to kind of, follow the complicated evolution to something as crazily complex as us. And I wonder, is there work are there any approaches going on that are aiming for much lower level cognition? I'm going to avoid the word intelligence to stop flame wars happening behind me. But
let's see. So two things. One is I want to say that I want to re-emphasize that we're not trying to build airplanes that flap their wings. Okay, so that's the important part of the machine intelligence is not identical to human intelligence. So I think here the response. So Turing picked language as the ultimate example, verbal behavior as the sign of intelligence, and nobody else talks. And in fact, a piece of language that goes back to Mark's question is that in using language, we have to take into account what's in the minds of others. So there are people who are building little insect robots that fly around and do things. no one's asking the think question of those. So you can build things that operate much like their natural counterparts. So then you might say to me, well, dogs think and cats think and maybe bees think. That's a different question. I think what Alan Turing had in mind was thinking and reasoning in the way that people do it. Okay. So, but not, and I think even Turing wasn't saying that we need to actually, so there's the behaviors that people do and there's the mechanisms they use to do it. I think even Turing was not saying the mechanism has to be the same. And I want to urge that the mechanism need not be the same for these reasons. But I think it was the kind of intelligent behavior, the kind of thinking that people do that he was after and that we're after.
Thank you, Barbara. That was wonderful. Let's give the...
This production is brought to you by the University of Edinburgh.